Let's talk about elastic potential energy. All right. So it's really stemmed from anything that obeys Hooke's law. And I'm using S for spring. It's an elastic force here, but I use the subscript E for electric. And so I'm going to use S here for elastic or spring. So the force is directly proportional to the negative of how far it is off of equilibrium. So if we have equilibrium at 0 here, then X would just be how far that is. This is known as Hooke's law, and K is the spring constant. And so if you want to look at the force from the spring, that the negative sign is indicating that if I stretch the spring this way, the force that the spring exerts is opposite the direction of the displacement. So this works for any elastic material, as long as it's within the elastic limit. And elastic limit gets into the very beginnings of material science, but if you take a material and if you stretch it far enough, you will eventually get past the elastic limit. In other words, when you let go, it will not go back to the original shape. So we're going to take a spring from some initial position x sub I to a final position x sub f, and the net force, looking at the net force coming from the spring itself. So in essence, this is the graph of what's going on. We're taking that we have some initial force and some final force related to the initial position and the final position. We're going to assume that the velocity and the position are both positive. In other words, it is on the positive side of 0 and the spring is being stretched in the positive direction. So the work done by the spring, it is conservative force, and so from one point of view, it's just the area under the curve. We'll get into the more calculus of it a little bit later. But the area under the curve is basically, I've got this trapezoid, and I need to find that area. So I'm going to break it up into the triangle and the rectangle. So the triangle, 1/2 base times height. Well, my base is the difference in the positions, and the height is the difference in the forces. Given the scenario, if this is indeed 0, the final force is a smaller number than the initial force, and so therefore that difference is a negative number. And over here we have Fi times xf minus xi. This is the area of this rectangle here, and Fi is a negative number, and so we end up with a negative piece right there. Going ahead and foiling, we end up with this, and then distributing that, we'll distribute the 1/2 to the first 4 terms here, and just bring those two down. Now we combine like terms. We have this Fixi and Fixf. So we'll combine those and we end up with this. We can factor a 1/2 out and get down to this particular part right here. Now we can factor out f sub f and f sub I, and ultimately it factors into this. And this right here, given the linear nature of that graph right there, this 1/2 F final plus F initial is just the average force. That's the value of the force, smack dab in the middle. And this XF minus XI, well, that's just the change in position. So we end up with the average force times this change in position. I know that the force is equal to negative kx, and so I can then take my previous equation where I had f sub f and f sub I and put in negative kx sub f and negative kx sub I. The rest is the same. I now factor k out. I'm left with xf plus xi times xf minus xi right here. Foil it out, you get the difference of perfect squares. So 1/2 k xf squared minus xi squared, and then you end up with this. And I know that the conservative work is equal to the negative change in potential energy, so that's negative uf plus ui. And it works if u is equal to 1/2 kx squared plus a constant, where this x right here is the displacement from whatever equilibrium is. Because if you recall back to initially, we started with this idea of x is equal to 0 at equilibrium, and so x, the position of x, is just the displacement from not only the origin, but also from a theoretical starting point. Now let's take a look at it from a calculus point of view. So we're just going to let x sub 0 be the position of equilibrium, so we're not going to worry about the specific case of this being equal to 0. but we can always check that at the end. But we have the spring force equal to negative k delta x, which is negative k x minus x sub naught. So this delta x right here, it's implied is the force is proportional of how far the spring has been stretched or compressed from its equilibrium position. I know that work is equal to force times displacement, and so since we're dealing with calculus here, the integral of f dot dx, which is negative k x minus x sub naught, bringing this into it, dot dx, we'll distribute this differential right here, and we're taking it from xi to x sub f. In other words, we have a spring at some initial position, we stretch it out to some other position, and we're trying to figure out what is the work done to stretch that spring. And x sub naught is equilibrium. So we have negative k x sub I, x sub f, x dx plus k, again, integral, basically distributing the negative k integral across the two differentials. Now notice that since we are pulling this thing in this direction, so dx and x are in the same direction, and dx and x sub naught are in the same direction. It's as if x is equal to 0 here. And it doesn't have to be 0 at this particular spot. It's just someplace not here. And we end up with negative 1/2 kx squared plus k x sub naught x, because again, x sub naught is a constant, because no matter where the spring is, that's still my equilibrium position. So I end up with this. I now go ahead and do the substitution part where I plug in the x sub f minus the x sub I. I'm assuming you've had enough integral calculus to be dealing to understand that without my doing more explanation. And when I plug in, I get this term right here. I'm just going to change the order around to get the x sub f terms together and the x sub I terms together. I then add and subtract this term right here. So I'm subtracting it here and I'm adding it here, so it's exactly the same quantity. And now I'm going to factor. I take my first three terms here, factor out a negative 1/2 k. I'm left with x sub f squared minus 2x sub naught x sub f plus x sub naught squared. And then I factor a 1/2 k out there and end up with this. I now have perfect squares here, so this is xf minus x sub naught squared and x sub I minus x sub naught squared. And then negative 1/2 k, negative, and then positive 1/2 k. As can be seen right here. So we have conservative work I know is equal to the negative change in potential energy, which is negative UF plus U sub I. And I'm going to set what we had just done, the work that we had just done, here equal to negative U sub F U sub I. And so therefore, this works if U is equal to 1/2 k x minus x sub naught, quantity squared plus a constant. If this got plugged into here and here, we'd end up with that. And so this is more commonly written as 1/2 k delta x squared plus a constant, and usually you set it so the constant is 0, but it doesn't have to be. And this delta x again is the position with respect to equilibrium. And I say position, that's really a vector and this is a scalar, but hopefully you get the spirit of what's going on there. So this delta x is how far an object is away from equilibrium.